Hello, this is Ray. We're looking at section 2.5. We are in our third objective where we take a look at what happens between two lines. So before we get to it, when we had our two equations and two unknowns version of finding out what happens with two lines in your algebra class or wherever you had it, you found that either the two lines were parallel or they intersect. And then there's another option where you had an infinite number of solutions, which is to say that both of the lines were exactly the same. So that's what happens in 2D. In 3 dimensions, different things kind of happen differently. So if you have two lines, it's possible that the two lines are parallel. That still exists, the idea of parallel. It's possible that the two lines intersect at exactly one point, and when they intersect, it's exactly at one point. And then it's also possible that the two lines are exactly the same. We actually won't be going over the two lines being exactly the same, but instead there is yet another option for looking at two lines in 3 dimensions. And the other option is that they're not parallel and they don't intersect. They are what we call skew. So skew lines are two lines that are not parallel and they do not intersect. And they're not the exact same line. So we're going to eliminate the exact same line scenario. And we're just going to look at when two lines are parallel, intersect, or the third option is when they're called skew. So here is our objectives. We're going to determine what happens to two lines if they're parallel, intersect, or they're skew. So if they are parallel, then it turns out that the direction vectors are parallel. Now, the direction vectors may not be exactly the same. One can be longer than the other, or the two vectors are going in the opposite direction. But as long as they are collinear, they're parallel, which means the two lines will end up being parallel. Then the other option is that the lines intersect. And if the lines intersect, they could possibly intersect at two different times. So that's a little nuance that we're going to work on when we do an example for this. And it turns out that if they are not parallel and they don't intersect, then the only other option left is their skew. And we won't have to test for skew. It's just by a process of elimination, not parallel, not equal. So not parallel, don't intersect. So the two lines are just not parallel and they don't intersect. So that's our only other option left. All right. Let's do an example. Here's an example where we have two lines. We have R1 and R2. Let's actually label it as R1 and R2. So let's call this sub 1 and let's call this sub 2. And then the first thing we want to check for is we want to check if the two lines are parallel. So check parallel. Let's do this off over here. Check parallel. And what we'll do is we'll extract the direction vectors from both of the lines and to see if they're parallel. Now there's a way to see if they're parallel by doing a cross product, but cross product is kind of it's not a very quick way of finding things if they're parallel. So an easier way to check if two vectors are parallel is to see if they're scalar multiples of each other. In other words, you can set one of the vectors, that's 3, -3, and 2, and see if this is equal to, not equal to the other vector, but rather a scalar multiple of the other vector. So if we can find a k that would work for each of the 3 components, then we can say, oh, they're just the scalar multiple of each other. All right. So if we solve for k using the first component, x, we get 3 is equal to -3k. So k must equal to -1. All right. So it has to be -1 for all of these components. So the second component is a -3 is equal to +3k, and that also works. K is equal to -1. But our last component, we have a 2 is equal to 0 times k. So 2 is equal to 0 gives no solution here. And so we're kind of out of luck, and we have to conclude that these lines, these vectors are not parallel, so therefore the lines are not parallel. So that eliminates the first option. For the second option, we want to see if they intersect. And generally, when we check for things intersecting, we want to set something equal to something. Well, the most natural thing to do is to rewrite these lines in terms of parametric form, and we'll set the components equal to each other. So if we write the parametric equations associated with these lines, for the first one, I'm going to get x is equal to 3 plus 3t. And the y would be 3 minus 3t. And then the z would be 0 plus 2t. Okay, so that's for the first line. For the second line, I will have x is equal to 6 minus 3t. The y would be 0 plus 3t. And then the z would be equal to 2 plus 0t. So that's just the constant 2. Now, the little nuance that's involved here is that the line, this line x, if they do intersect, this line for the first line, R1, may have a point here where this R2 would also have a point. But it's possible that the point for R2 will hit that line at a different time. So what we want to do is we want to account for the possibility that the time for line 2 to hit this point of intersection might be different from the time that line 1 will intersect. So what that means is that we want to change this parameter into a different parameter, and usually we use something like s as a different parameter to work out. Okay, so we will set them equal to each other, as we have already mentioned. So set these equal to each other, and then we'll proceed. We have a 3 plus 3t is equal to 6 minus 3s. Now I'm changing the parameter for the second line. And then we have 3 minus 3t is equal to just 3t. And then we have 2t is equal to 2. Oops, I'm sorry. The second one here should have been an s. The last one, z, is equal to 2. There's no s's, so we don't need to worry about that. Now we have 3 equations. We have 2 unknowns. So good way to solve, there's a lot of different ways to solve for this. A good way to solve for this is to take 2 equations at a time and solve for t and s, and then plug that into the third equation to see if you get a result. So what I'll do is I'll take this first line, this last line here is easy to solve for. T is equal to 1. I will box that and say, hey, that's one of the solutions, possibly. We'll take t is equal to 1 and put it into the second equation. 3 minus 3 times 1 is equal to 3s. And then solve for s. So 3 minus 3 is 0, is equal to 3s. So s must equal to 0. And that seems to be our value for s. Let's take our value for t and our value for s and to see if we put it into our third equation that it would be equal. And so I have 3 plus 3 is 6 on one side. I have 6 minus 0 on the other side. So yes, it is equal. So they intersect. Graphs, the lines intersect. And once you get them to intersect, we're done. We don't have to check for skew, because that's if they intersect, then that is the the result of the two lines. So it's one or the other is not just, it has to be one of those three possibilities. So the lines intersect. Just for the sake of viewing this, let's take a look at the graph of this. I already drew the graph. So these are the two lines, right? And then, oh, we didn't find an intersection. Sorry, I got a little ahead of myself. So the line intersects. Let's find the intersection. To find the intersection, we have two possible ways of doing it based on the solutions that we found. We could take t and put it into the first equation. So we'll put t in there, and then we'll solve for x, y, and z. So if I put t in here for x, I'm going to get x is equal to 3 plus 3. 3 plus 3 times 1, which is 6. Y is equal to 3 minus 3 times 1, which is 0. And z is equal to 2 times 1, which is equal to 2. So 602 seems like it's going to be our intersection. You can also put s and put it back into here. Since s is equal to 0, that might be a little simpler. You could have also, since we have our original equations written in vector form, you could have also put the s is equal to 0 into the original equation, and we'll put that as s, and then that's going to be 602 again. So regardless of how you find your point, the point of intersection should be the same regardless of what you use. So back to the graph that I was excited to look at. These are the two lines, and the point 602 seems to be our intersection, so you can see in a lot of different angles that that is in fact the case. All right, so what I'll do is I'll do a trace for them. So I'll do a trace for the first one. I think this is the first one, 3 minus 3t, t minus 3 minus 3t, and 2t. And I'll do a trace. So as I trace this, I see that I'm going to hit that point when t is equal to 1, right? When t is equal to 1. All the other points would just be along that line, but t is equal to 1 is that one place where I hit that point. Now, if I take this one, if I move this around, I will hit that same point at t is equal to 0. So we have t is equal to 1 and t is equal to 0. Those two lines hit that point at different times, and that is the reason why we wanted to split this up into two equations and change the variable for one of the equations. Okay. Let's do another problem just for the sake of contrasting, and let's do this problem where you have your lines written in a different form. This is our symmetric form of the line, and let's see how we can work with that. So we're going to want to extract the point and the direction out of this, or mainly the direction, and we want to see so basically what we want to do is we want to write this in parametric form so we can find the directions, and then if they're not parallel, we can see if they intersect. So remember that to get to the symmetric form, that each of these things are equal to t. So we can incorporate the t in there. So we have t is equal to x minus 3 over 2. And if we solve for x, we will get x is equal to 2t plus 3. Okay. And then similarly, for the y is equal to t. So 2 minus y. So y must equal to, there'll be negative t, but then I'll have to switch, so it'll be 2 minus t. And then similarly, z z minus 1 over 3 is equal to t, so z must equal to, this is a 3t plus 1. And it's good if you have the t's kind of next to each other or on top of each other, so you can kind of extract the point and the direction. So it looks like for R1, for line 1, I have my point 321, and my direction is going to be the coefficients. That's 2, -1, 3, and this is going in a t direction. All right, let's do the same thing over here. Out of the x, we will get 4t plus 2, 2 plus 4t. Out of the y, we will get 2t and then -1, but then you have to change it around. So this will be 1 minus 2t. We should check that to make sure that's correct. And our z is equal to 2 plus 3t. Okay. So we can find our R2, and that's equal to 212 as our point. And then the direction vector is going to be 4, -2, 3. So that's our equation for this. And to check if they are parallel, check parallel. We want to take our direction vectors and see if they're scalar multiples of each other. We have 2, -1, 3. We want to ask if this is equal to some scalar multiple times a second vector, 4, -2, 3. And I see that this is 2 is equal to k times 4. So it looks like k is equal to a half. And is that going to work for the second one? The second one also works. -1 is equal to k times -2. So if k was 1/2, this will also work. But the last one, I have 3 is equal to k times 3. And so k has to equal a 1 in that case. So we got no 1k will work, so this is not parallel. All right, so that's the first part. Now let's see if they intersect. And remember from the previous example, we saw that we needed to change our one of the variables into an s. So let's change this into an s instead of a t, and then let's rewrite our equations. So our equation for x is going to be 3 plus 2t is equal to 2 plus 4, and then I'm using a different parameter there, s. I have 2 minus t is equal to 1 minus 2s, and then a 1 plus 3t is equal to 2 plus 3s. Okay, so these are the three equations that we're going to work with. And again, many different ways to do this. I'll do this similar to the first way I did it. Well, first let's write it into a nice set of 3 equations and 2 unknowns. Let's write the t's and the s's on one side. So let's have a 2t minus 4s, and then this is equal to 2, and then subtract the 3. So 2 minus 3 is -1. I have a negative t here. Bring the s over, so I have a positive 2s. And then I have a 1, and then subtract the 2. So 1 minus 2 is -1 also. And then the last one, a positive 3t. And bring this over to the other side, negative 3s. And this equal to 2 minus 1 is positive 1. All right. So we'll work 2 equations at a time. I'll take these 2 equations and I'll keep the first equation the same. 2t minus 4s is equal to -1. And this one I will multiply this second equation by 2. So it's a -2t. Multiply this by 2, I get a positive 4s. And multiply this by 2, I get a -2. And if I add them, I will get 0 and 0 is equal to, add them, get -3. So 0 is equal to -3 already gives us no solution. So we don't even have to find the third equation, work the third equation into this. This already does not work for us. So we can say, because there's no solution, these two lines do not intersect. The lines do not intersect. So if they don't intersect, then there's only one possible scenario left, and we could say lines are skew. Okay. I do have a graph for that. Let's take a look at the graph for this particular scenario. So this is the work that was done. Let's take a look at the graph. I have these two graphs, and if you look at it from there's one, or not one, but there's angles that you can look at it where you can see that they clearly don't intersect. So if you look at it one way, it looks like they intersect at a point, but then if you look at it in this way, kind of like this way, it doesn't look like they intersect. It looks like this one line is higher than the other line. They're going from -10 to 10. Maybe if we go make them longer, -20 to 20, -20 to 20. So you can see that they really do not intersect. I guess this is a good view. So they're not parallel, but they don't intersect, so that must mean that they're skew. So that's the scenario for that. Okay. All right. I hope that helps in finding out what happens if you have two lines. And that's it. Good luck.